Hello everyone. In this video, I'm going to talk about geometric sequences. This also goes under the term of the exponential growth model, although it can also be a model where you have something called exponential decay, depending on this common ratio. So this is sort of AKA, also known as exponential growth model. So what is a good example of a geometric sequence? You can think of like cell division. So imagine you have a single cell, you have one cell, and then it splits, and then you get two cells. Okay, and then so this is time one, time two, and then each of those two cells split, and time three you get four cells, and then each of those four cells split in two, and you get, well, how many? Eight cells. So if I were to imagine this sort of population, P sub n equals the population of cells after n splits, well, let's see. After zero splits, we just had one. That was our time. Well, maybe let me do this. I'm sorry. Let me make this time zero, time one, and time two just to conform with the usual notation. So P naught is one. We just have one cell. P1 after one split, we have two. P2 after two splits, we have four. After three splits, we have eight. And what you can see is what's happening is we're doubling each time. So this gives us a recursive formula that if you want to take that step from the n minus first population to the nth population of cells, we just multiply by 2 each time because each of the cells in the n minus first population turns into two cells, and we get 2. So this is the recursive formula, and there's an explicit formula that comes in here as well. There's an explicit formula. And the explicit formula is an exponential type formula that p sub n is in fact equal to 2 to the nth power. And you can see that just by putting in the values 0, 1, 2, 3, you'll get p to the 2 to the 0th is by definition 1, 2 to the first power is 2, 2 to the 2 squared is 4, 2 cubed, 2 to the third power is 8, so on and so forth. So this explicit formula can be used to compute the value. Now, if you had not started with only one cell, if we had started with 5 cells, then you would see that the next step would be 5 times 2, and the step after that would be 5 times 4. In other words, you would have multiplied each term in the sequence by that starting number of cells. And that gives you a general definition of a geometric sequence, which I'll give here. So a geometric sequence is a sequence, and again, I'll use these p values, p naught, p1, p2, on and on, satisfying a recursive formula, p sub n is equal to r times p naught, times p, not p naught, p n minus 1. This is the recursive formula, r times p. This is the recursive. And there's an explicit formula as well. The explicit formula is that P sub n equals P naught times R to the n, R to the n. This is the explicit formula. Either formula works, they're both true for your geometric sequence. This number R that occurs in both of the formulas, here and here, that number is called the common ratio. R is called common ratio. Just like in the arithmetic sequences, we had the common difference. This is called the common ratio. So there are a lot of geometric sequences that you can have, but let's look at one example. So let's say we have the following geometric sequence. We will use 2 again, and I'll just start with 1/2, 1, 2, 4, 8, 16. So my P naught is 1/2. This is P1. This is P2, P3, P4, P5. I'll be able to go up in this graph to P4. So let's see. Let's see how it looks if we plot this. So I get P naught is 1/2. It's sort of right around here. And again, I'm going to put the subscript, I'm going to think of that as time. That's going to be along the time axis at the 0 position. P1 is 1. And it doesn't look like much is happening. I'm just kind of going up a little. P2 is 2, still not much happening. And then all of a sudden, it starts getting big fast. P3 is 4. I've sort of doubled. And then really, P4 is 8. And P5, I can't even draw. It should be way up here. And you can see if we were to connect these dots, we get this real, seems okay at first, but we get real quick growth. And this is this notion of exponential growth, is that it's not just kind of going up like a line. It's really just starts shooting up and getting out of control very quickly. And so this is a common property of geometric sequences. However, you can have an opposite property if the common ratio is not greater than 1. So if it's less than 1, it goes sort of decays very quickly. All right, we'll look at that now. So you can have, let's look at a similar situation, but we'll go to the following pictures. Let me copy this. Oops. So let's look at one more example before we move on. I'm going to remove this particular graph, this line graph, and move my points back down so that I can play with them. So this one that we just looked at had a common factor of 2, or common ratio, pardon me, of 2. So here we had R equaling 2. What happens if we have something like R equaling let's say 1/2. So let's try r equaling 1/2, and we'll start with some large value. So let's say not large, we'll try to fit it on our graph. So we'll say 12. Okay, so if we start with our population equaling 12, and then we half it, we're going to get to 6. This is using the recursive formula, is that we just multiply the previous term by 1/2. And then we half that, and we get 3. And we half that, and we'll get 3/2. We half that, we get 3/4, 3/8. Okay, it starts to get pretty small quickly. All right, let's see what the plot looks like. Starting in the beginning at P naught, we're way up at 12. We half it. Okay, that's not too bad. But it is pretty sharp decline. Then we're going down to 3. Then we're going to go down to 1.5. Then we're going to go down to 3/4, which is less than 1. And then, okay, we can keep on going, kind of half of that. You can see it's really going to get Notability won't let me do it exactly at the half, but no, struggling here. Yeah, right around there. But you can see when you connect these up, that, yeah, it's rapidly approaching 0. You're getting very close to 0 very quickly. And this is known as exponential decay. So we talked a second ago about exponential growth, but here we have this notion of exponential decay. And this is this is a common type of population, or well, commonly modeled when you have something like considering half-lives and things of that sort. So how much maybe a particular substance, how long a particular substance takes to break down into I don't know, other atoms or other uh, sort of molecules, things of that sort. Um, okay. So this is the idea of a geometric sequence. Um, these things are we'll see this kind of sequence occur in many models, and we'll look at these types of sequences in some financial mathematical applications later on in this course. So understanding this particular kind of sequence will help us a lot when we try to apply these sort of time models to other scenarios and other situations. Okay.